So we're now going to use this current version of the program as a starting point, prototype for things that we would like to add to complete this lab. So we already have this directive extern that introduces the name of beep to our code, and the linker is able to find this code in kernel32.dll. So some portability concern, I'm going to skip this right now, but basically you can read that our program is completely rooted in a Windows operating system, and therefore the program, of course, is absolutely not portable in any way to another platform, unless you will be making changes to the names of the calls and parameters and so forth. This is really a Windows specific program at this stage. So things to do, we would like to change the values here, this array of values, to a 32-bit double word, because this double word, I believe, we're going to use as, so we're going to change it to double word, D word, and we're going to use this array as frequencies in hertz, right? So we can initialize it to certain frequencies. For instance, we can initialize it to 500. Okay, so frequencies in hertz. So we can name this values thing frequencies. So every CPU instruction in the program should have an appropriate comment. You can see that I'm trying to follow. I'm trying to do my best to annotate every instruction with some sort of comment that explains what it does. We would like to use const memory segment for all constant values. So far, I just having just one variable here named endLine, which we used in previous laboratory exercise to mark the endings of the lines. We should be using the operators as appropriate. I already tried to apply this length off to the values, and now the values have become the frequencies. So let's change this. And so replace load effective address instruction by move. So let's just basically move into ESI. We can load offset of frequencies. So this will be faster than computing effective address at runtime, which was the idea of load effective address instruction at the very beginning. Add console input output to prompt for user input, and have user input a certain number of values. So we'll be asking the user to provide basically a number of beeps to make, and prompt them for frequency values in our program. This note is very important. We kind of took care of it, that we took care of the preserving the registers, because beep function could modify a lot of registers, and specifically it modifies EX, EDX, and ECX. So we just use this push all double word registers on the stack to preserve them. In the future, when we discuss stack handling, we'll cover it in detail. But for now, this is the way to preserve all general purpose registers, and it needs to be accommodated by the corresponding pop instruction, which restores the values of all registers from the stack. So also add the logic to handle potential beep error codes. So the function, when function fails, it returns the value in register EAX. Okay, so we need to be able to get last error if EX is non-zero. So here for, let's just say that we can handle errors. Okay, so there could be some invalid frequency values or duration values that cannot be handled by beep, so we can handle the errors. So we can basically test EAX, as we discussed earlier, against itself like this, or EX and EAX, and if it's not zero, right, we can jump to no error, or we can jump forward to an anonymous label. We can create this anonymous label right here like this, and basically complete the work of beep by simply checking the value of EAX and jumping forward. So otherwise, what we could do, we could handle the error by calling getLastError. And getLastError needs to be decorated like this. It doesn't take any parameters, so its decoration should be like this, getLastError. And we'll also add extern for one second for this getLastError. Okay, looks good. And so we'll be calling getLastError, which will get the error code in EAX. So the program can display this error code on the screen. So for now, we'll just say that once we getLastError, we can say that the error code will be loaded in EAX upon return. And what we need to do is display the error code. So if there is no error, we'll just proceed forward, and we'll just get out of here, pop everything here, and return. Otherwise, we'll display the error code in AAX. So that's just something that that remains to be done. But this is how you would call getLastError. Let's build this just to make sure that the syntax is okay. So there's this error in directive right here. Yes, I forgot to add that this is also a near procedure. That's just a qualifier that needs to be added in the flat memory model. So let's do that. And there is still a syntax error. Of course, we need to make a call right here. Okay, so this is a call instruction build. Okay, so... and we still haven't changed everything, so we'll change everything to frequencies right here. And in fact, since this is now compiles fine, this is an example of handling errors, let's just finish this by adding a comment here that if EAX does not equal 0, right, the idea is then everything is okay, right? Otherwise, we call getLastError, and we will be displaying the error code on the user screen. So this would be the appropriate type of comments here. That the idea here is that we want to check EAX for non-zero, and if it's non-zero, then everything is fine. All right, so here let's just maybe update some of these frequencies in a loop. So we are going to load a loop counter into register BL. We're going to initialize the data pointer to frequencies into register ESI. And instead of computing the sum of these values right here, what we could do is that we can just simply move into register EAX. So basically we can just do calling this beep in this loop. Okay, so what we can do is we can load frequencies, but this time we'll be loading it from frequencies at the offset specified by ESI. Actually, no, let's do it this way, right? So just basically use ESI as address. So we'll say get frequency. And for now, duration is 500 millisecond, which is half a second, and we'll just say hard-coded for now. Okay, so that is hard-coded. We're going to make a beep, and this time, instead of incrementing ESI, because it was designed to work with bytes originally, now it became D-word, so we need to be really, instead of incrementing, we'll be adding to ESI, I'll say type of double word, right? So which is going to give me this operator type is going to give me the size of each integer. So that should be incrementing ESI by the size of each double word here. So this basically resolves to the value of 4, because double word is the length of double word is 4 bytes. Decrement BL, this is just a loop counter, so it stays the same way. If BL is not 0, we're going to continue and making beeps, otherwise we're going to just remove this for now and trying to now organize the loop. And so we don't need the EAX right here. So right now we're just going to add a comment here, is that we're going to generate beeps from the array of frequencies in memory, right? So we're going to scan this array of frequencies because we're loading its initial address, the address of the initial double word, the initial integer right here in this array of 16 integers, and we're going to make this loop to generate these beeps. So this is not going to be very interesting, but it should work. So let's just make sure that we have this section of the code highlighted right here. And so this loop now will accomplish what this assignment is asking us to do, to generate a series of beeps. And we're also added already call into get last error in case if there was an error. Let's see if we can build this program, and let's try running it. I'm pressing Ctrl F5 to just launch the program and see how it works. So for some reason the program did not terminate correctly. So let's find out what is happening here.